everybody. We're going to talk about document clustering using entropy methods today. Thank you for attending the talk. So let's start talking about text clustering. It's an important part of pre-processing and processing. It's related to organizing information, to dimension reduction, to improving times and quality of information retrieval and systematic browsing. Also for semi-supervised classification methods. Now, what are common methods used for text clustering? First, we start with the most common representation for text, which is the vector space representation. I recommend the book by Otazo, for example, for introduction on these subjects. Documents are thought as vectors. Vectors which are constructed based on the presence or absence of certain words over a common dictionary. We can also choose more informative words, strategies such as TF, IDF, which are based on information methods. After we do this procedure, we end up with document term matrices where rows are documents and columns are terms. These representations are in high dimensions and sparse. And typically, there are more informative subspaces which have lower dimensions. So, what are common methods once we have this vector space representation? Then we can use k-means or centroid methods based on L2, L1, or Mahalanobis distances, which are the most common ones. Or we can think of spectral methods related to our more informative subspaces. Or we can use density methods based on bins. Or we can use kernel methods, which are very interesting because actually what you do is you map your observation space to a feature space, and that's very related to spectral methods. Now, typically, documents are more complicated than this bag of words or vector space representation. I can indicate the articles by Schenker and all and Markov and Last, very interesting start points for this. Because there are relationships among words, and these relationships allow us to think of text as graphs. Each document is thought as a graph where these relationships are apparent. We can think of a more complicated way of doing this based on conceptual graphs. I'm not going to talk about this today, but it's just that when we think of text as graphs, we can include more complex situations. So we want to construct graphs from text. We can construct them, for example, based on L distances among the words. We're going to try some of these L distances in our application further on. We can think of word order, or we can think of morphological, syntactic, and semantic characteristics, also conceptual, as we were talking about before. So once we have this representation, if we want to cluster text, then actually we're talking about clustering graphs. How do you cluster graph? Well, the first thing you have to do is create some kind of distance among graphs. And typically the distances we talk about are related to graph-edit or random walks or kernel distances. And there's a very interesting book by Eureka and Wang where they relate all these different possibilities for calculating distances. However, these methods are slow for big graphs. And think we're talking about text, which is related to maybe thousands of words of this sparse representation, and so this can be slow. But also in our context, we have the extra problem: we have many graphs because we're dealing with many documents. So we're going to as multi-level graphs, and well, there are many ways of introducing these concepts. There's a very interesting book from the beginning of this year by Lasega and Schneiders, also the articles by Kibela and other authors. So in this context, we think of documents as a collection of graphs, not one graph, but as a collection of graphs, which are constructed over the same nodes, that is, the same words. But we could think of more complex situations based on some kind of hierarchical relationships. Again, think about concepts or context. So we're talking about graphs, in our case, which are created over the same nodes, but we could do this more complicated. Now, information is in stack, and we want to find some kind of dimension reduction technique for a collection of graphs. So this is where entropy methods come in, and we'll follow very closely the work done by Domenico. They were interested in other problems. They weren't interested in text, but they looked at these entropy methods for graphs, and actually their work is based on the ideas by Deborah and other authors, which considers associated to a certain graph the Laplacian, which is actually the renormalized adjacency matrix minus the diagonal. We'll call this the Laplacian. And once we have this structure, then the von Neumann entropy is defined as the entropy over the spectrum of this matrix associated to the graph. This von Neumann entropy will be small if there's no mixture. And that's behind the idea of what we're going to use for clusterization. So now we have we generalize our von Neumann entropy for one graph to the stack. And if we have a series of aggregated layers or documents in our stack, then we'll define the von Neumann entropy as the sum over the individual layers, over the individual Laplacians associated to each one of these graphs. Now, we have our stack, and we're going to choose an aggregation of layers, that is, our clusters, that maximizes Q, which is actually the distance from the completely aggregated graph to a certain aggregation. So, more precisely, our function Q for a certain aggregation will be 1 minus the mean entropy for our certain series of clusters over the entropy of the completely aggregated graph. A good aggregation will separate layers that have more mixture than if they are aggregated. So again, we have our von Neumann entropy for the stack, and Q, very interestingly, is related to the Jensen-Shannon divergence. We'll call this GS of cluster 1 and cluster 2. If this divergence is small, clusters should be aggregated, and if it's big, no. The greedy approach to complex optimization then can be thought as doing a hierarchical clustering with this divergence. So we'll apply our method to a series of tweets, and they were related to hashtag election 2016, and we did it on Friday, November 11th, and in November 25, sorry. We selected 60 tweets just to make things readable. All our pre-processing and clustering was done in R. The procedure can be slow because we're calculating the spectra for big sparse matrices. So one of the ideas that in order to optimize this procedure was approximately the number of effective eigenvalues we need for each graph associated to each document. And we're going to see for 5, 10, 20, and 30. Actually, of course, that depends on the complexity of the underlying dimension of our documents. But for this example, for our 60 tweets, which are short, we're going to use this number of effective eigenvalues. So the other thing we're going to look at is choosing the graph method. Whether it's just the adjacency matrix, the original, whether words are or are not in the same Twitter document, or methods based on L distances. That is, there will be a relation among two words in a certain document if they are closer than a certain distance L. So, checking graphically, of course there are other methods of doing this, but for this presentation, checking how our clustering is going on, we're going to use heat maps, dendrograms related to the heat maps, and word cloud. So we'll start with selecting K. We see in using tools, few values of effective eigenvalues, it leads to a non-good approximation. The graph starts getting flatter, but still we're choosing the trivial solution, that is no clustering, if we're using too few eigenvalues. However, if we use enough, here we have for 20, then it sounds reasonable. It sounds like a reasonable approximation, and it's not too different with what happens if we use 30. So we thought it was a good idea to stop with 20. The second thing was we select our distance. Again, we can use 2 distances, 5 distances, or 15 distances. We're going to choose 2 distances because it gives a non-trivial solution, which the other two don't. So we're going to choose two distances. And finally, we can compare what happens for this example with our two distance and our adjacency relationship. And we see that this confirms the original intuition for text. More complex relationships that just belonging to the same document is relevant for clustering. Finally, our cluster. So again, just a different vision of what we just talked about. Our heat maps for just using the adjacency matrix, and on the other hand, the graph or matrix associated to two distances, and we actually see a more clear clusterization structure if we use our two distances. Last thing we wanted to show then were the word clouds for both procedures. On the left then we have our adjacency, and to the right we have the two distance. Now, work in progress, what we're doing now is looking at different graph from text methods, including more structure. We're looking at different aggregation methods. Here we just use the sum. Faster calculations of the Jensen-Shannon divergence matrix, which can be done by improving sparse matrix eigenvalue calculations. That's one of the things we're doing, or looking at approximate divergent matrix using random projections, and finally distributed schemes using Spark, for example. Finally, the other line of work is related to other approximations, not the Jensen-Shannon divergence for optimizing function Q. Well, we hope you enjoyed our talk. Thank you. Bye-bye.